I'll get started. Let me see if I'm starting late so I know to go over.
A little bit.
Oh, I got to go 2 minutes over today. All right. I'll begin with a word of prayer. Dear Father, we thank you again for this opportunity we have just to meet and study your creation. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. I have another example for you guys of the singular value decomposition. It is the example from the book, but it's a good example, so let's cover it. So, example 1. So the matrix A is given, and the goal, our mission, should we choose to accept it, is to find the singular value decomposition of A. All right, so let's do that. So the first order of business is to calculate A transpose A, because the eigenvalues of this matrix are what are called the singular values. Now, this works out to minus 9, minus 9, 9. Then we need to find the eigenvalues of this guy. So we got determinant of lambda I minus A transpose A, also known as the determinant of lambda minus 9, 9, 9, lambda minus 9. I'll put some dividers in. Sometimes I like to put dividers into the matrix just to see it better, you know. Anyway, so that is lambda minus 9 quantity squared minus 9 squared. Difference of squares, so that's lambda minus 9 times lambda minus 9 plus 9, also known as lambda minus 18 times lambda. So apparently eigenvalue is 18 and then 0. So this tells me the singular values are the square root of 18, and so he in the book I noticed that they said sigma 2 is 0, but this is the only non-zero singular value. Now that's not really the language I used last lecture. I insisted on the singular values being non-zero, so my apologies. I may have added that from the usual nomenclature, I guess. Anyway, the non-zero singular values are the interesting ones. Now, once we have that, you can easily calculate that A transpose A times the matrix times the vector 1 minus 1, and you can calculate A transpose A times 1, 1. And if you look at those, it's fairly obvious what you get, right? Like, if I do A transpose A, this matrix times 1 minus 1, I get 18 minus 18, right? And the other one, I just get 0, right? So this implies I should put V1 equal to 1 over the square root of 2, 1 minus 1. That's an eigenvector with eigenvalue 18. And we can put V2 equal to 1 over the square root of 2, 1, 1. All right. So in short, find that the V for the singular value decomposition is going to be given by like 1 over root 2 minus 1 over root 2, 1 over root 2, 1 over root 2. All right. That's an orthogonal matrix, and it's an orthogonal matrix formed, let me write it down in a sentence here. So this is orthogonal matrix formed by orthonormal eigenbasis for A transpose A. It's not for A, but for A transpose A, right? Why can we always do this? Why can we be assured that such an eigenbasis exists when we're doing this calculation?
A transpose A is symmetric.
Very good. A transpose A is symmetric, and as such, it is orthonormally diagonalizable. That's a mouthful, right? So then what? Well, so then we calculate AV1. So AV1 here is 1 minus 1, minus 2, 2, 2 minus 2, and I'm multiplying that by 1 minus 1. And then, you know, I like to pull the 1 over root 2 out front because it's annoying to, like, why have 6 1 over root 2's when you can just have 1, you know? So keep those annoying scalar factors out front while you're doing the calculation, would be my advice. Now, what happens then is I get 2, I get minus 4, and I get 4. Right? And likewise, if you calculate AV2, what do you get? We get 0. All right? So unlike the example I did last class, we don't have, like last class, when we did this, we found a U1 and a U2. And the M was equal to 2, because like last time we did a, so this is a 3 by 2, right? So in the last exciting episode, what did we do? We did a 2 by 3, right? You know, it was like this, rather. And so for that one, we had like AV1 is you know, AV1 over sigma 1 was U1, and we had AV2 over sigma 2 was U2, and that was it. We were done because that got us the 2 by 2 matrix big U, which we needed for the SVD, and that was it. But this time, what are we expecting here? So like, just to recap where we're going, the SVD, singular value decomposition, has the following form. It says A is equal to U sigma V transpose, right? Where the sigma has the form D and then zeros. And D here is sigma 1, sigma 2, sigma R, where R was the rank of A. It's the number of linearly independent. Well, anyway, it's the rank of A. So, what's the trouble here? For this one, we can form our U1, right? U1 is equal to AV1 over sigma 1, right? And sigma 1 is sigma 1's that. So I've got I got myself what do I got here? Sorry guys, 1 over square root of 2 times the square root of 18, yeah, times 2 minus 4, 4. What's that? So what's square root of 2 times square root of 18 is square root of 36, yeah? Oh, by the way, because the grader didn't know certain things about like mission 7, like the 9 in the power series, some of that thing, so those sort of things, I just added 2 points to everybody's mission 7. So like the number you have on the page is not quite right. I just added 2 points. If you feel like you have been slighted in a particular fashion or form, do come talk to me after class. I can probably give you a point back. So, you know. So anyway, that's the square root of 36, which is 6. So that ends up just giving us 1/3 minus 2/3 and 2/3. All right, so there's U1. But here, you know, so for AM by N, what's the story here? U is M by M. This guy is M by N. And V transpose is also n by n. That's the size of things we're looking for here, okay? All right, so how do we find the rest of it? How do we find the rest of u? Remember, I mentioned to you guys that the singular value decomposition is, what's the word? It's not unique, right? And I think a good part of the non-uniqueness comes from what we're about to do right here, right? So we have u1, right? And it is 2, it is 1, 1 minus 2, 2, with a third out front for normalization, basically. And we need to find u2 and u3 that are perpendicular to u1. How should we do that? I like the singular value decomposition as a topic that we end with in this course because it has like so much of the stuff we've learned this semester, right? Matrix multiplication, transposition at the start, finding the eigenvalues and eigenvector for a matrix, multiplying a matrix times a column vector, right? And then, even this, we find ourselves tasked with the problem of extending a basis, which is one of the more probably theoretical, probably the most theoretical, sophisticated thing we've done in this course is this thing right here. How do you extend a basis? And I don't think I've really taught you a method either, yeah? So, you know, you're kind of left to ad hoc measures, I suppose. But there is something we can do here. Any ideas? What's that?
Problem 60.
Problem 16? Problem 60? That's a funny suggestion, but no. Because there we need we'd need 2 vectors to do that. But I'd be right with you. Like in calculus 3, if I ask for a third vector, which is not in the plane given by 2 vectors, we know what to do. We take the cross product, but we just got 1 vector. We need other methods. How do I find perpendicular vectors to a given vector? This is something you probably should know the answer to, leaving this course. So let's write it down symbolically. We're asking the question, u1, we want u1 dot x equals to 0, right? For x equals to u2 and u3, which we don't know, right? Our goal is to produce these guys. But that's just a linear equation, right? So that's nothing more than like, you know, 1/3 of, let's see here, x1 minus 2x2 plus 2x3, right, equals to 0. What's the solution set to one equation and 3 unknowns? Like if I had given you this equation at the start of the course and asked you to find the solution set, it would have stopped some of you dead in your tracks because you've been like, well, what? There's just one equation. What do you do? What you do is, I'm going to solve for x1, you know. x1 is equal to 2x2 minus 2x3, right? So my x is equal to 2x2 minus 2x3 comma x2 comma x3 for x2 and x3 in the reals, right? That's the solution set, things of that form, but then we can do better, right? Do better. Oh, I'm sorry. Excuse me for saying that. I just feel wrong. I should tell people to do better. That's something idiots say. 1, 0, do better. How about you shut up? All right, x3 minus 2, 0, 1. There you go. That is, of course, that's the basis for the null space of what? Let me put it in other words. We want u2 and u3 to be in the null space of u1 transpose. That's what we're doing. All right, so the basis for that null space is these 2 vectors I just found. Right? So let's say u2 prime equals to 2, 1, 0, and u3 prime equal to minus 2, 0, 1. Now, What's the problem? What kind of basis were we looking for? I guess I haven't completely said it yet, have I? Well, I shouldn't complain. We are getting closer to graduation. The cough is still here. I had to be careful. I'm almost all better. Be careful. If I get all better, it's all for naught. So these, you know, these need to be orthonormalized, right? I want them to be orthonormalized. They need to be normalized, right? And orthogonal. So, well, U2 is easy enough. So U2, I just do 1 over square root of 5, yeah? 2, 1, 0. Now that's normal. Woohoo! Is U3 perpendicular to U3 prime and U2 prime perpendicular? They're not, right? Dot product of these two is non-zero. So what do we do? If we want to take a given set of vectors and make them orthogonal, what do we do? We run the what? Gram-Schmidt algorithm. So let's do that. So we'll do U3. I guess I should say prime prime in my usual lingo. I forget what my lingo was. It's U3 prime minus U3 prime dot U2 prime divided by U2 prime dot U2 prime times U2, I guess, prime. All right, so what is that? That's U3 prime was minus 2, 0, 1. Excuse me. What's the dot product of U2 prime and U3 prime? Can you guys tell me? What's that? -4? Cool. So we have minus -4. So I guess that makes it plus. And then what's U2 prime dot U2 prime? It is 5. And then U2 prime, of course, is 2, 1, 0. So this gives me a unpleasant 1/5. I'll bring the 5th out front. And that gives me a minus 10. Minus 10 plus 8 is minus 2. And then 4. And then 5. So normalizing this thing gives me U3 is 1 over the square root of 45 times minus 2, 4, 5. So at long last, here is your singular value decomposition. A is equal to your U, apparently, is, where'd the thing gone to? 1/3 minus 2/3, 2/3. My U2 was 2 over square root of 5, 1 over the square root of 5, 0. My U3 was minus 2 over the square root of 45, 4 over the square root of 45, and 5 over the square root of 45. I normalized that right? 25 plus 16 is 41. 41 plus 4 is 45. So yeah. And then my sigma. What's D here? D is dumb. D is just a 1-by-1 matrix. You know, the D is just this. It's the 1-by-1 matrix, square root of 18. And so we've got square root of 18. And what else? And this is supposed to be a what? The same size as the original matrix. A was what? Lost track. 3/2. So I'm supposed to have 18, 0, 0, 0, 0, 0. And then you got your V transpose. V transpose. V1 transpose, the little V1 transpose is the first row. So I got 1 over root 2 minus 1 over root 2. And then I've got 1 over root 2, 1 over root 2. So here's your U. your sigma and your V transpose. This is the singular value decomposition of A. Any questions? So actually, like there's so much in this one example. It really does combine many techniques, right? You got eigenvalues, you got the Gram-Schmidt algorithm, like I said, matrix multiplication. There's tons here. And on the other hand, if you're given a singular value decomposition, you can like, well, sometimes you can solve. See, I wish I brought my book with me. I'm a little fuzzy on what the definition of the Moore-Penrose inverse is. Oh, thanks. What I'm a little bit leery of is, ooh, this one's pretty. What I'm a little bit fuzzy on is whether the Moore-Penrose inverse was defined for a rectangular matrix or just a square matrix, you know? That's what I can't remember. So this is in section, it's the end of the section on the singular value decomposition here, the Moore-Penrose inverse. It says when sigma contains rows or columns of zeros, a more compact description. No, so it does not have to be. It does not have to be. Does not have to be square. So suppose that your singular value decomposition looks like this: U r, U m minus r, d 0 0 0, and then you've got over here you've got what we could call VR transpose, and then V n minus r transpose. And so this is an r by r. In this context, the Moore-Penrose inverse is A plus is equal to V r d inverse u r transpose. So this is the so-called Moore-Penrose inverse. And it's the next best, so like suppose your matrix is not invertible. Suppose your matrix is not invertible. Well, the Moore-Penrose inverse is the next best thing to an inverse which doesn't exist. So it's just based on, let's see here. So for this, let's see if we could write it down for this example. What's my, r is just equal to 1, right? This one just has r. The Moore-Penrose inverse is exceedingly silly for this example. So r is equal to 1, all right? So r is equal to 1, which means this ur is just u1, and the vr is just this. And so the Moore-Penrose inverse here is exceedingly silly. It's just VR. This is V1. This is V1 transpose. Yeah. So it's just V1. What's D inverse? That's 1 over the square root of 18. What's the inverse of a number? It's reciprocal. And then UR transpose is just, well, U1 transpose. So it is literally 1 over the square root of 2 times the vector 1 minus 1. And then you've got 1 over the square root of 18, which I'll bring out front. So we have 1 over, fine, 1 over the square root of 2, 1 over the square root of 18. And then U1 transpose, which was, let me put that 3 out here too while I'm at it. I hate fractions, let's keep them all up front. 1 minus 2, 2. So it's like 1 over 9 times 1 minus 1 minus 2, 2, 2 minus 2. So there you go, that's the yep.
Shouldn't that be 1 over 18?
Where?
Instead of the 1 over 9.
Oh yeah, 3 times 2 is 6, isn't it? Good grief. It's not 3 to the second power, it's 3 times 2. Yeah, thank you. Very helpful. Now, what?
It's supposed to be
Oh, did I do it? Did I still do it wrong?
18.
Oh. Yeah, this is not good. All right, I'm going to stop talking about this. I should just accept your correction. There we go. Listen, this has applications to the least squares problem. You can just straight solve the least squares problem using the Moore-Penrose inverse. If you look at the end of the section, it explains how, but since I'm saying stupid stuff, I'm going to stop. All right, so I hope I've given you enough. I mean, this is pretty much it. The two, so like, let me just tell you, in the take-home test, the two problems, there are 3 problems on the singular value decomposition in the take-home test. 2 of those problems are very related to the book problems. They're not exactly the same as the book problems, but they sure aren't far from them. I'll just say that. All right? So in other words, I've done examples in class which are very, very close to your 2 of the SVD problems I gave you. The other one, I'm hoping, isn't too bad, but it is different. So anyway. All right. Any questions while I get my stuff together here? So some of you have come and asked me for help on mission 8, and I have let you take a picture of the solution to one of the problems. So if you're such a person, do feel free to share the wealth with others in the class. I do not mind that, of course. I wouldn't have shown it to you if I didn't want other people to see it too, obviously. Any question? Or no? Just stretching. I'll allow it. All right. So the next topic in this class. So up to this point, believe it or not, I have behaved. So I would say, well, everything that I've talked about, with the exception, so like, there's just a deficiency in linear algebra books. Undergraduate linear algebra books are afraid of including a proper calculational section on the Jordan form. It drives me nuts. It's not really much more sophisticated than the stuff that's in the usual books, but it just, for whatever reason, gets left out. And it's really, really dumb to leave that out, because it's leaving you guys, without a full tool set. It'd be like being a carpenter and not having a router or something. I mean, it just didn't make sense. So like, because not every matrix is diagonalizable, right? So if you want to understand how to solve problems, if you have a problem which comes to a linear system, and you want to understand what the structure of that system is most deeply, you need to have tools which allow you to, take matrix apart into its fundamental form. And you shouldn't be stuck, oh, I can only do that if the matrix is diagonalizable, And so if we have the Jordan form, we can rest assured that any matrix is similar to a matrix in real Jordan form. That's a completely general method. Also, the singular value decomposition is a completely general method. We did not make any presuppositions about the structure of A. So this is a totally general result, which is, and so kudos to the book for having a section on that. I just really think they should also have a section on the real Jordan form. And I don't know why, but they just refuse to, which is really dumb, because it actually is more important for differential equations, as I hope I've communicated to you, to solve systems of differential equations. The real Jordan form, coupled with a matrix exponential, gives a complete answer, which I think every engineer should know about, because you guys solve linear systems of differential equations all the time if you're doing any kind of actual math in your job. Now, some of you, of course, will inevitably never do any more thinking. You'll just sit back in an easy chair and let the AI do the work. But let's pretend that's not the world we're living in. So, well, until some other guy learns how to put 5 AIs to work and puts 4 of you out of business. But as the case will be. Actually, I really do think we should have a class here that teaches you guys how to use AIs wisely. To actually implement it. Like, you shouldn't be writing code. AI should be writing code for you. That would be smarter. My brother said he got ChatGPT to write a Python script that was pretty decent. And since he knows how to write Python, it was a simple matter for him to fix it. Now, this is not a class I could teach. That's not my skill set, But I've been trying to talk Dr. Wang into doing it. I think he'd kill that class, But anyway. Okay, so all that was a preamble to say now I'm going to misbehave. So I want to talk to you guys about algebra and matrices. And this is not the algebra that you might be thinking of. So when I talk about an algebra, let's say A, this is a an abstract set with multiplication. Let's use a star symbol for it for just a second. And that multiplication satisfies a lot of the usual rules. For example, if I have like x plus y star z, you guys tell me what should happen. What do you guys think should happen? How about this? X star z plus what?
Y star z?
Y star z, right? This is the distributive property, right? You have that. If this is a real number, all right, then you ought to be able to pull it out of this multiplication, right? And the kind of algebras I'm interested in are what are called associative, which means that this makes sense. To make it a little bit more precise, you can put parentheses in, right? So it's an associative algebra. I also like my algebras to be what are called unital. A unital algebra is one such that there's some number 1, let's say 1 in A times x is equal to x is equal to x times 1 sub A. All right. The algebra is also such that, like, if I had x and y in the algebra and c was a real number, then cx plus y is again in the algebra. So to put that into words that I'll talk more about next class for you guys, that would make the algebra what's called a vector space. A vector space is a space in which you have scalar multiplication and you have vector addition. And it satisfies laws like we've seen in Rn. So another way of summarizing everything I'm telling you at the moment is an algebra is a vector space paired with a multiplication. I'll repeat that. An algebra is a vector space paired with a multiplication. So what are some examples of algebras? This one I hope you're familiar with. We could have A equal to the complex numbers, right? So if you look at like Z equals to X plus IY, and A equals to, W equal to A plus IB, how do we multiply complex numbers? We got like Z times W. So first of all, the star, I'm just trying to, and I'm using star there to be a little bit abstract, but like in examples, oftentimes instead of using star, we use what's called juxtaposition. So in other words, Z star W is just ZW. So this is juxtaposition. Juxtaposition is the usual notation we use for complex multiplication, as opposed to some silly star. And you guys already know how to do this, right? I hope so, because I gave you homework which assumed it. You know? So if you didn't know how to multiply complex numbers, I'm sorry. But anyway, I do still have some expectations like high school math. I haven't given up on them completely yet. XB plus YA. So there you go. That's the definition, if you will, of complex multiplication, right? Complex numbers are an example of an algebra. Are there others? Well, another one that I've studied a lot with students in the last decade or so is what are called hyperbolic numbers. Now, other people object and they say, no, it's really the Clifford algebra 1-0. That's how I imagine they talk, but I'm used to being rude. X plus, I've never met them, so it's a safe thing to do. X plus jy and j squared is equal to 1. See, this you could say x plus iy such that j squared, oops, my bad, I squared is equal to minus 1. Now I realize you electrical engineers, your j squared is equal to minus 1, but your j is not my j. In fact, I use j not, I do use j as a somewhat, it has different meanings in different examples for me. But here j squared equals to 1. And so the way you multiply hyperbolic numbers is like this. So you got yourself xa plus yb plus j times xb plus ya. All right. So hyperbolic numbers are interesting. The reciprocal in the hyperbolic numbers works like this, like 1 over z is equal to actually x minus jy divided by x squared minus y squared. So when can you find the inverse of a hyperbolic number? Let me ask it a different way. If the hyperbolic number is non-zero, does it have a multiplicative inverse? The answer is most assuredly yes, because the complex calculation up here is x minus iy over x squared plus y squared. Does a non-zero complex number have a multiplicative inverse? The answer assuredly is yes, right? Because x squared plus y squared is non-zero. What about x squared minus y squared? Can x squared minus y squared be 0? Sure can. If x is equal to plus or minus y, you're in trouble. So the hyperbolic numbers are annoying in that they have 0 divisors. So like all of the numbers like here and like there, this y equals x, y equals minus x, everything along those lines cannot be inverted. So when you try to do like the analog of calculus 3 over the hyperbolic numbers, if you try to make a straight analogy to the calculus I'll teach in complex analysis, you run into a lot of trouble because you got these 0 divisors that are in the way of our usual constructions, unfortunately. Now, I see I'm about to write on the middle board and then I was about to put the screen down. That would have been dumb. Let's not do that. So over here, you might wonder what this has to do with, what does this have to do with this course, right? What does this have to do with linear algebra? And I would say the main, well, there's a couple things. One is history. History has, a lot of the foundations of engineering math. It was born from some of these things, actually. To make that explicit, I need to talk to you guys about what's called a representation. So if we have an algebra, all right, then we can basically represent it with what I call M of A, all right? And just for the sake of specificity, I'll suppose that my algebra is actually equal to Rn as a point set. Then you have M, this mapping that goes from your algebra to the representation of the algebra, which is a subset of Rn by n. So here, this is a map. Big M with feet is a map. And big M of x times y has to be equal to big M of x times big M of y. So this over here is matrix multiplication. That over there is algebra multiplication. And this is what's called this is called the regular representation. Of the algebra. And so like I've showed you guys the regular representation of the complex numbers. So, the regular representation of the complex numbers was this, x plus iy. You actually do that 2 by 2 complex matrix. X minus y, excuse me, xy, my bad, xy minus yx. That's the regular representation of the complex numbers. Those 2 by 2 real matrices multiply and behave like complex numbers. For example, you can check this out. Like m of 1 is equal to what? 1, 0, 0, 1. M of I, what's that equal to? This one, right? And you can check that that 2 by 2 matrix, which I sometimes call big J, squares to minus the identity, right? So that 2 by 2 matrix behaves like the complex number I. And so that's a follow-up on example 1. A follow-up on example 2 would be the matrix representation of hyperbolic numbers. It's the same thing without the minus. And in this case, the matrix representation of the hyperbolic number j is simply 0, 1, 1, 0. This is the matrix whose square is the identity. All right. And we actually calculated the matrix exponential of that thing, and we found it was Cauchys and Cinch's. Not an accident. Not an accident at all. Because you can prove for the hyperbolic numbers with the natural definition, if you do like e to the j theta, it works out to Cauch theta plus j sinh theta. That's the hyperbolic analog of Euler's identity, which is e to the I theta is cosine theta plus I sine theta. There's all kinds of really, really cool stuff like this to discover. I had some students discover it on their own, and then we had the misfortune of looking at Wikipedia, and we found out, oh, it's all been done before. But it felt good to discover it on our own, and after about like 6 months or so, three to 6 months of the students working together and stuff, like I realized that they had recreated, I don't know, 40–50% of a couple of PhD theses from like the 1940s. So I was kind of happy. Wasn't bad. Now they had the benefit of modern notation and modern mathematics. And back in the 1940s, it was all this sea of like AIJ kind of stuff, indices and such. So you can write down all of this to say that you can define something called quaternions. That's really what I was going to talk about today, but I don't have too much time left. I think I've got just enough time to do it. What I probably don't have enough time to do today is show you, what I wanted to show you is you can define explicit 4x4 matrices which satisfy the algebra of the quaternions. So a quaternion, H, has the form T plus xi plus yj plus zk, such that t, x, y, and z are real numbers. So the idea of the quaternion, so these were discovered by Hamilton, arguably. Hamilton, like Hamilton of Hamiltonian mechanics, I believe. Hamilton, 1843-ish. And he spent a decade finding these. And the reason it took him a decade was the better part of that decade, he was trying to, so like, think about this. C is to rotations, so R2 is equal to C, right, as a point set? As R3 is to rotations, how? That was the question that was more or less the framing that Hamilton asked himself. Is like, okay, so if the complex numbers corresponding to rotations in the plane, right? Every complex number can be written as a dilation, that is a rescaling times a rotation. That's the polar decomposition of complex numbers, which you'll learn in complex analysis if you take it with me. So what about 3? R3, is there a way to talk about R3 in terms of rotations in 3 dimensions in the same like algebraic way? 'Cause complex numbers, really nice algebra. We see it all the time, right? How about R3? Is there an algebra that will encode the 3-dimensional rotational structure that we've seen like in this course, right? We've used eigenvectors in 3 by 3 matrices for it, right? That's not an algebra. It's something else. And the answer is no. You cannot find a 3-dimensional algebra which implements rotations in 3 dimensions. It's actually impossible. This can be proved. Perhaps I'll prove it in 321. I've tried to prove that in 321 before, but then I got tired at the end of the course. So it happens. The ultimate answer to this, Hamilton found, was to, instead of doing a 3-dimensional algebra, he realized, no, I actually need a 4-dimensional algebra to implement 3-dimensional rotations. And so was born the quaternions, which originally had been thought of as time and space. That was their interpretation. It still is their interpretation for some people. Engineering and science was all done with quaternions before the advent of vectors. These predate vectors by like 50 years. And so the basic rules here are kind of funny. I squared, j squared, k squared, these are all -1. ij is equal to k, jk is equal to I, ki is equal to j, but ji is equal to minus k, kj is minus I, and ik is equal to minus j. What does this look like? I hope it strikes you as the cross product, right? I cross j is k, and so forth. In fact, the reason that you guys use ijk, where did ij and k, where in God's green earth did ij and k come from in Calculus 3? The answer is Hamilton's quaternions. That's why they're used there, because it's in honor of Hamilton's quaternions. If we say that the quaternion z equals to t plus xi plus yj plus zk is, let's say, equal to t plus vector r. Right? In other words, I call this piece vector r, just for the sake of notation. It's interesting, and if I have w equals to, let's say s plus vector, I need another letter, v, let's say, then you can calculate zw, and you'll get a formula involving the dot product and cross product and more, involving the s, the t, and the v and the r. I'll do that at the start of next class. We're out of time today, unfortunately, but because the quaternionic product implements both dot products and cross products, we could use quaternions to write all of the equations that you know and love from engineering and science, right? So why did we give up on quaternions? It's because vectors are just better, all right? I mean, I'm sorry, but it's just a better notation. And sometimes you don't want to do dot and cross products all at once, right? But there are still people who love quaternions with an almost religious devotion. You'll meet these people. They're called geometric algebraists. Anyway, that's all for now.